everybody. Welcome back to Measure Theoretic Probability. I am so glad some of you returned. In the last video, we saw what was perhaps the most amazing example of a two-dimensional set ever witnessed by mankind. And it was a blob that looked like this. And we talked about ways to measure this set. And we talked about maybe computing the area or the length of the longest line that we can fit inside this set, or the area of the smallest circle in which this can be inscribed. And I'm sure you have many more good ideas, and I know I do. So I thought in this video, we would set some ground rules. Can you and I agree that when we measure this set, we're going to return a number? Not a letter, a number. And maybe can we agree that we're going to return a non-negative number? And I don't know, other things like if we put another set completely inside this set and we measure both sets, maybe the set inside should not have a larger measure than the outside set. We're going to see the formal mathematical definition of a measure in the next video. Right now, we're still talking about those special sets that are actually going to be called measurable sets, but right now they're called sigma fields. So remember, we had a non-empty set omega, which could be anything. It's a set of things, objects, numbers, high dimensional, low dimensional. And in our running example, we flipped a coin twice and omega contained the outcomes: heads, 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 tails, tails, heads, and tails, tails. If the coin is fair, or if we know how biased it is, then we can compute the probability of getting, for example, heads, tails. And we can expand that to compute the probability that we get maybe heads, tails, and tails, heads. And we can do that by knowing the individual probabilities. So we can just assign probabilities to subsets of that sample space and use that to expand to all subsets of the sample space. And that's what we were looking at last time. We called them fields or sigma fields. Those are different things. So a field was a collection of sets with three properties. Number one, it has to contain the full set omega. Number two, it has to be closed under complements. And number three, it has to be closed under finite unions. And then we kicked it up to a sigma field, which is a collection of sets, subsets of omega, which number one has to contain omega. Number two has to be closed under complements. And number three has to be closed under countable unions. So this includes finite unions, but also allows us to go to infinite unions as long as we can index them and count them, like 1, 2, 3. And that was a sigma field. And these are going to be the sets that we're going to focus on when we define a measure. So a measure is going to be a function that takes in a set and spits out a number. For example, if you're using Lebesgue measure, which is the typical measurement that people use in 2 dimensions, this would be area, then the Lebesgue measure you can think of as a function that takes in this set and returns the area. So all sigma fields are fields because the property 3 of a sigma field is a stronger condition than it is in the definition of a field. But we looked at an example at the end of the last video of a field that was not a sigma field. And we demonstrated that it was not by taking a countable collection of sets in the collection we were looking at and unioning them. It was an infinite but countable collection of sets. And we produced a new set, and it was not in the original field. And therefore, we did not have a sigma field. And so this raises the question for us: can we just throw that set in to make a sigma field and maybe anything else we might need? So starting with a collection of sets, if we don't have everything we need in there for it to be a sigma field or even a field, can we throw things in until it becomes one of those? That's what we're going to talk about today. So I want to start off with a non-empty set omega, and I'm going to let A be a collection of sets. So I know my handwriting is not that great at distinguishing these. I'm going to use a capital Roman A with kind of really straight edges to denote an event or set, like the event that you get at least one tails. But I'm going to use a kind of curly A, just like a kind of curly F, kind of calligraphy, to denote a set of sets or a collection of sets. And so I was saying this is maybe not so distinguishable here, but I think within context of the problem we're talking about, hopefully it won't be an issue. So we've got a non-empty set omega. We take a collection of subsets. I'm going to call this A. And then we're going to define the sigma field, or equivalently sigma algebra, generated by A as the smallest sigma field that contains all the sets in A. Now, I'm not sure that's completely well defined yet because of this idea of measuring and what is small and what is large. But the basic idea is you have a collection of sets and you find that you're missing things, like you union something up and it was not in there. So you put it in, and the smallest sigma field is going to be that we put in the bare minimum of what is needed. Although I do have a more formal definition coming up. We're going to use this sigma of A to denote the sigma field generated by A. Here's a fun fact for you. Suppose that we have a non-empty set omega and we have a sigma field F, and that we have a set A that's a collection of subsets of F. Then I'm going to look at the sigma field generated by A, and I claim that it's in F. And maybe at first this seems obvious, but if you think about it for a few minutes, I don't think it seems obvious. Let me try to use a graphic here. So I've made this big bubble, which represents the sets in the collection F, which is a sigma field. So you can imagine this filled with sets. And for what I'm about to say, we should think of smaller and larger as area here, which is just a heuristic for understanding what I'm trying to say here. I also have a subset of the sigma field, a collection of sets that I'm calling this curly A. And I want to look at the sigma field generated by A. And we know that has to contain all the sets in A and probably contain some more things. So I'm going to draw it like this, kind of expanding A out a little bit. And the way I've drawn it, the sigma field generated by A is not contained in F, but I claim it must be. So what's going on here? The reason this cannot be the picture of the sigma field, a depiction, this is not really a picture of anything, it's just kind of a graphic, is because we are going to see that the intersection of two sigma fields is again a sigma field. And so if F is a sigma field out here and sigma of A by definition is a sigma field over here, then the intersection, which is right here, is also a sigma field. And it also contains all subsets of A, and it's smaller. So if we assume that a sigma field generated by a collection of sets in a sigma field A is not fully contained in that sigma field F, then we get this contradiction. We can actually find a smaller sigma field. So we have shown the fun fact that if F is a sigma field and A is a subset of F, which is a collection of sets, that the sigma field generated by A is completely contained in F. And we used the fact that we've yet to prove, so I want to do that now, that if you intersect two sigma fields, you get another sigma field. And in fact, we can have a more formal definition for the sigma field generated by A. We can define the sigma field generated by A as the intersection of all sigma fields that contain A. So I'm writing it like this, an intersection of Fs, and all the Fs must be sigma fields that contain A. I am making a leap here because I'm about to prove that the intersection of two sigma fields is a sigma field. And by induction, you could stretch that and say the intersection of a finite number of sigma fields is a sigma field. But this doesn't have to be a finite number, and it doesn't even have to be a countable collection. So if you'll bear with me for a little bit on this, I just want to claim that the intersection of even an uncountable collection of sigma fields is again a sigma field, although we're only going to show it for two. If you're going to make any sort of definition like this, I define it to be the intersection of all the sigma fields containing A, then you need to make sure there's at least one, or the definition is kind of meaningless. And we know we have at least one, and that is the power set, which is the set of all possible subsets of omega. Before we go forward, I just want to make a clarification if need be. You may not be thinking this, but I just want to make sure you understand that a set in the intersection of two sigma fields, F1 and F2, does not have the form A1 intersect A2, where A1 comes from F1 and A2 comes from F2. The sigma field is a collection of sets. And for something to be in both collections, the entire set needs to be in both collections. So we're never intersecting these individual sets when we're trying to intersect two sigma fields. You can see in this picture, I've got these circles representing sets in each of the two sigma fields. And in this particular picture, I have two of them in the intersection, but I'm not intersecting circles from F1 with circles from F2. Okay, so let's prove the fun fact that the intersection of two sigma fields is a sigma field. And for this to be true, I need to clarify a little bit more. They need to be sigma fields with respect to the same underlying set omega. So complements in each need to be complements in omega. Do they contain the full omega? It needs to be the same omega for F1 and F2. So suppose that F1 and F2 are sigma fields with respect to omega. Number one, to show that it's a sigma field, we want to show that it contains omega. Because F1 and F2 are individually sigma fields, they both contain omega by property 1. And therefore, the set omega is in both of the sigma fields. So it's by definition in the intersection. So we have shown that omega is in the intersection. Number two, we want to show that the intersection of these sigma fields is closed under complements. So take any set A in the intersection of the two sigma fields. That means it's in both sigma fields F1 and F2. But because those are individually sigma fields, a complement is in both F1 and F2, which means a complement is in both F1 and F2 and therefore in the intersection. So we're done. We took a set in the intersection and showed that its complement also has to be in the intersection. And the countable union, very similar. So if we take a countable list of sets, A1, A2, A3, possibly infinite, but nice and listable in the intersection of our two sigma fields, then all of these sets are in the first sigma field and all are in the second. And therefore, because those are sigma fields, they're closed under countable unions. So the unions of all of these A's are in F1 and in F2, which means they're in the intersection, which means that the intersection sigma field is closed. Well, we're showing it's a sigma field. So this means that the intersection of the sigma fields is closed under countable unions. So we've got property 3, and we're done proving that the intersection of two sigma fields is a sigma field. I have another fun fact for you, and that is that if you've got a space omega and you have a collection of subsets A and another collection B, so I tried to make this like a big curly looking B, that the sigma field generated by A must be contained in the sigma field generated by B. This is one of those things that maybe seems obvious and actually maybe seems hard to prove because it's a little bit too obvious, because you just kind of don't know, you kind of are just thinking, well, of course this is true, but how would we show this? So first of all, I want to point out that the collection of sets B is contained in the sigma field generated by B. And that's by definition because the sigma field generated by B is the smallest sigma field that contains all the sets in B. So definitely contains B. And so because the collection of sets A is contained in the collection of sets B, and this is contained in the sigma field generated by B, we now know that the collection of sets A is contained in the sigma field generated by B. But the sigma field generated by A is the smallest sigma field that contains A and is in fact the intersection of all sigma fields containing A. So one of these is sigma of B that contains A. So that's going to be thrown into the intersection, which means when we find the sigma field generated by A, it's going to be maybe the same as the sigma field generated by B or smaller, because the sigma field generated by B, we're going to intersect with other things. So looking at smaller and smaller pieces of it potentially. So that's how you do it. We're done. We've shown that if you have a collection of subsets A contained in a collection B, that the sigma fields generated by each have that same direction of containment. Now we're going to look at 3 examples of sigma fields generated by collections of sets. The first 2 are going to be pretty trivial, and the third is going to be super important in real analysis and measure theoretic probability and other areas of mathematics. So to start, my collection of sets, this large curly A, is going to consist of one set, just some set A. We already saw that we can generate a sigma field from one set by throwing in its complement, the empty set, and omega. And so this is a special case. The sigma field generated by the big curly A here is just the sigma field generated by the one set that it contains. A second example, I don't know if you would call this an example, but if F is a sigma field, then the sigma field generated by F is just F itself. In other words, it's the minimum stuff you have to throw in to build up to be a sigma field, but it's already a sigma field. So we don't throw in anything. The sigma field generated by a sigma field is that sigma field. And the third one I promised you was important. So the space here, the non-empty space omega, is going to be the real line. And I'm going to let this curly A be the collection of all open intervals of the form open A to open B. The sigma field generated by these open intervals is a very famous sigma field known as the Borel sigma field or sigma algebra, and the sets in there are known as Borel sets. Now, I've already used a kind of script, large, puffy, curly B as a generic collection of subsets of omega, but now, from now on, I'm going to reserve it for Borel sets. Okay, so now that we've seen how we define the Borel sigma field on the real line as generated by open intervals of the form open A to open B, let's take a look at some other things that are in there. For one, we have all half-closed, half-open intervals of the form closed at A, open at B. And to see this, we need to try to find a way to construct this interval out of open intervals. So without regards to the actual endpoints and letters, let's just look at an open interval. If you take the complement, you get something that looks like this with, closed, but going off to minus infinity and plus infinity. And then you can intersect that with another open interval, which leaves you with this piece right here. So if that's enough to convince you, great. But if you're doing a homework problem where you have to be really constructive about this, if you want this to be A and this to be B, you just have to work your way back up this series of pictures. And you'll see that you need to choose some numbers C, D, A, and B ordered in that way. Start with the interval from C to A, take the complement and intersect that with an interval from D to B so that you end up with closed A to open B. Another type of interval we have in our Borel sets is the half open, half closed of the form open on the A side and closed on the B side. And this is a totally symmetric argument to what we just did. Other intervals that are contained in the Borel sets are closed intervals of the form closed A to open B. And there's many ways to generate each and every one of these examples. But in this case, I'm going to take the half closed, half open intervals. I'm going to go closed A to open B unioned with open A to closed B, and that will give us the entire interval from A to B inclusive, so closed A to closed B. We can get singleton sets, so sets that contain a single point. And there's many ways to do this. If I want to just get the point A, which you can think of as the closed interval from A to A. So one way to get this would be to assume that we've already showed that we have closed intervals, and then you can just say the closed interval from A to A is that point. But we can also do it like this. We can take the open C to closed A and intersect it with the open A to closed B. We saw both of these are in the Borel sets, and the intersection is the singleton point. So we have just shown that this singleton, the point A, is in the Borel sets. If you want to do this in a fancier way, then look at the intersection of closed A, so that's something that contains A, up to A plus 1 over n open on that side. We are intersecting a bunch of intervals, the first of which is A to A plus 1, the second of which is A to A plus 1 half. So if you intersect them, you get the smaller interval, A to A plus 1 half, intersected with A to A plus 1/3. And when you intersect that with the previous interval, you get something even smaller, A to 1/3, et cetera. And we're going to keep shrinking down that right endpoint and always including that left endpoint. And we're going to be able to rule out having anything up above A if you take n large enough. So the infinite intersection here is going to reduce to the singleton point A. Those are just some examples of things that are included in Borel sets. There are a lot of different kinds of sets in there, some very strange looking. And I do want to say that not all subsets of R are in there. We will eventually see examples of subsets of R that are not Borel sets. But now I want to look at potentially generating Borel sets starting with a different collection. So we started with all open intervals of the form open A to open B, and we could have started with all closed intervals of the form closed A to closed B. How can we get the open intervals back? From this closed interval, we know we can get singleton points because the singleton point A is the closed interval from A to A. And if that's in there and we're generating a sigma field, then the complement of singleton points is in there. And so we can get the open interval from A to B by taking the closed interval from A to B and intersecting with the complement of the singleton A and the complement of the singleton B. So this is how we got from a closed interval to an open interval. So I do know that starting with closed intervals of the form closed A to closed B, I can at least generate everything our original definition of the Borel sets can generate. And I know I haven't thrown extra things in because we've already seen that starting with the open intervals, we will get the closed intervals. So you don't have to worry about closed intervals giving us the open intervals and also other stuff. it's going to generate the same sigma field, the Borel sets in R. Other intervals that can generate the Borel sets are these infinite intervals from minus infinity up to A inclusive. I need to show that starting with something like this, I can get open A to open B, and therefore I could get anything that I would have gotten starting with open A to open B. And I also need to show the other direction. So I need to show starting with open A, open B, that we can get to sets or intervals of this form. I'm going to leave that second direction to you as an exercise, but let's see if we can get open A to open B. First, note that we can write open A to open B as a union as n goes from 1 to infinity of open A plus 1 over n to closed B minus 1 over m. And, the first element in this union, well, if we have the open interval from A to B, this implies that A is less than B. We don't really talk about intervals that are ordered the wrong way. And if you start this union, the first term is going to look like A plus 1 to B minus 1. And that may not be a proper interval in that the left endpoint, A plus 1, could actually easily be bigger than the right endpoint. If so, you want to start this union from 2. And if that first interval isn't in there, you want to start it from 3. And eventually, given a fixed A and B, you'll be able to go up high enough here to start an infinite union of intervals that make sense. But yeah, this infinite union is open A to open B. You can see that A is never quite included here, but you can get as close as you want to it. And we're moving to B from the left side. So we're taking an interval that's actually inside what we want and kind of stretching it out, but never quite making it to B. So this gives us open A to open B. What does this have to do with what I started with? I wanted to show that I can get open intervals from intervals of this form, not this form, but I can write intervals of this form, I claim, using intervals of this form. Let's take a look. The interval just a little bit above A and a little bit below B, open on the left and closed on the right, could be constructed by thinking of this closed piece right here as the right endpoint of a half infinite interval from minus infinity up to that piece. And we can intersect this with everything outside of a minus infinity to closed interval looking something like this. So if you take everything outside of this, then you get open from this point on up and intersect that with closed from this point on down. And that'll give us the A plus 1 over n to B minus 1 over n that we needed in order to put together in the union on the previous slide. And that infinite union will generate open A to open B, which was the entire point of this exercise. If you want to be a little more specific about it, we can write the open A plus 1 over n to closed B minus 1 over n in this form. So this is exactly what I just said in pictures, but written a little more formally. Here's a really fun fact that we're not going to show today. We just showed that starting with the intervals of this form, we can generate the Borel sets. We actually only showed one direction, but we could also use intervals of this form and restrict A to only being rational numbers. And the reason for that, if you know about this, great. If you don't worry about it. But because the rational numbers are dense in the real numbers. So between every two real numbers is a rational number. That's what it means for the rationals to be dense in the real numbers. And you want to use that sort of property to do what we just did again, but this time restricting A to be rational, which I think is kind of cool. Borel sets are so much more than an example of a sigma field. This is the most important sigma field in R and is easily generalizable to R2, R3 on up. And even though we're studying measure theoretic probability and not just real analysis, Borel sets are going to be super important to us as well. So stick around. In the next video, we're finally going to define a measure. So I hope you come back.